Next up, we have the one and only Jeff Dean. There's probably other Jeff Deans in the world, but this is the one we all know. Jeff's done a lot of work. He works at Google as a senior fellow. Obviously, he's been involved in a lot of papers and Usenix and all the systems conf, MapReduce, Bigtable, Spanner. I mean, the list goes on. The quick aside I always give is that there was one day, and he'll probably unfollow me after I say this, but one day some years ago, I was at a bar with Chris Nickeljohn, who some might know. And literally, I remember I see like, oh, Jeff Dean just followed me on Twitter. Something good must have happened. And then, Chris was like, just wait an hour, he'll unfollow you. And he has still followed me to this day, probably until today. So thanks, Jeff, for doing this. And please kick it off.
My pleasure. So I'm going to share my screen in a minute. But what I thought I would do is give a bit of a reprise of a talk I gave a few years ago at a 50th anniversary of SOSP, or operating system, maybe 25th anniversary, I forget what it was. But basically, sort of my talk in that was highlighting sort of progress in the cloud computing space over the last kind of 20-ish years. And so that's roughly what the talk will be. And I've extended it a bit to talk about machine learning systems, which I think are, obviously of considerable import these days. But with that, I'm just going to launch in, and then at the end, we'll do some questions. So share my screen. Here we go. Share that. And there we go. Fantastic. I hope you can all see my slides. So I'm going to talk about the rise of cloud computing systems. I think
Jeff, no, we can't. Hold on, Jeff, hold on. I need to fix it.
Okay. Let me know how
I need to fix it real fast. It's not capturing correctly.
Oh, it says I am sharing the screen, so.
Yeah, I saw it over Zoom. It looked okay. I guess it's just on Twitch.
Oh, okay.
Twitch is not made for all this funness, maybe.
One streamy thing into another. Excellent.
How did it just?
You see that, correct? On Zoom, please.
Jeff, I can see your entire.
Yeah, that's fine. That's fine.
Go ahead and start sharing again. Go ahead and put it in the way you want it, and then I will grab that. Okay, so you're doing that. All right, and then I'm going to go live and grab it. So hold on just a second. Okay, you're good.
Okay, we're ready to go. Everyone can see the slides, I hope. And I'm going to talk about the rise of cloud computing systems over the past, 20, 30 years. So first, I think it's good to take a quick look back. The idea of having large-scale computational systems that people then can share and use is not new. So I think the Multic system in '65 was basically a way for people to have utility computing. And I think the current cloud systems of today are really kind of a much larger scale manifestation of the vision that was originally outlined by Multics. And if you look back at the earliest days of Google, one of the things that Google believed strongly in was that we wanted to use significant amounts of computation in order to sort of tackle the problem of organizing web pages and making them searchable and useful. And so this was kind of the very earliest days of Google when it was a Stanford research project, and Larry and Sergey would sort of, their advisors were very mean and would not sort of buy them enough computers, so they would go down to the loading dock and intercept machines destined for other research groups and volunteer to set them up for the other research groups, and then sort of live off the float of like using them for a month before they actually deliver them to the other research groups. It means it's a pretty heterogeneous set of machines because different research groups would buy different things. And to where we are today, so this is like a nice professional photograph of a large-scale Google data center. And these are the systems that are sort of incredibly relevant in these times where large amounts of computation happen, and many, many different kinds of clients and customers all run computations on these shared services. And if you peek inside, it looks like a giant sea of racks and racks of machines, many, many football fields. You can choose your American or international definition of football, but they're pretty big. And so how do we get from there in 1965 with Multics to where we are today with kind of these really large scale systems? And so prior to kind of the mid 1990s, if you look at the kind of subfield of operating systems research of distributed systems, that work kind of tended to emphasize modest scale systems at a single site. So like the Grapevine work at Xerox PARC and others, as well as kind of widely distributed decentralized systems like DNS, which kind of sits at the heart of much of how we communicate on the internet. And then there were adjacent fields like high performance computing, which has like a supercomputers or things like Crays and other kinds of computational devices like that. Very heavy focus on performance, but not much focus on fault tolerance, whereas distributed systems tended to be, we assume different pieces of the system can fail and we want to sort of handle that nicely. And then another adjacent field is transactional processing systems or database systems, which have this strong emphasis on how do you manage data, particularly structured data, and provide consistency and nice high-level APIs for accessing that data, and tended in the past to have limited focus on the absolute largest scale systems, especially at low cost. So you can buy very large database systems from commercial vendors, but they tend to charge a fairly pretty penny for that. So the caveats for this talk are, I'm just going to kind of give a surface level overview of a bunch of different things, and I can't possibly cover all the relevant work. I'm going to focus on a few important areas that I think have happened over the years, and systems and trends, and I'll describe the context behind the systems with which I'm most familiar. So that's the ones that I know the best, so I can just give you kind of more insight into what we were thinking about some of those systems. Other ones where I cite them, but I wasn't involved in the work, I will not be able to give you that context, but I will do my best. Okay, so what caused the need for these giant sort of football field-sized sets of computing systems? And I think one of the things that happened in the kind of late 90s was all of a sudden we had these very resource-intensive interactive services like search that provided the key motivation for trying to bring as much computation to bear on these kinds of problems as possible. And the growth of the web in the area of search, in particular from millions of pages to tens of millions to now hundreds of billions or even trillions of pages, and the desire to index all of that data and then search it millions and then billions of times per day, all with sub-second and ideally like sub-tenth of a second or quarter-second latencies, actually means you need lots and lots of computation in order to accomplish all this, both kind of ahead of time to do the indexing and the crawling, and then at serving time in order to actually accomplish the goal of very quickly giving the user what they want, given what they just typed in the search box. So Google was not obviously the first search engine. I think one of the earlier search engines was the Berkeley Now project, and there were a bunch of others, but the Berkeley Now project in particular emphasized the use of lots and lots of computers in order to accomplish the goal, provide the underlying computational substrate for a search engine, unlike other search engines, which were tended to be single system initially, and then a smaller number of large systems. And so the Now work was very influential, and that eventually became the Inktomi company, which provided search services kind of as a white label product for other companies, and used a bunch of Sun workstations kind of brought together with interesting software in order to make them appear as more of a single computational platform. So my vantage point is when I finished my PhD at the University of Washington in 1996, I decided I would join DEC World, which was a small research lab for Digital Equipment Corporation in Palo Alto, ironically, only 2 blocks apart from DEC-CERC. So the nice property that had was I could go visit people at CERC, and there was a gelato store in between. And one of the things that had come out, the reason I decided to join Whirl was basically it was a relatively small research lab of 25 or 30 people, but it had a whole bunch of different kinds of projects being worked on. And one of them was AltaVista, which was a search engine collaboration between both CERC and Whirl and NSL, a different research lab 1 floor below us. And when I joined, AltaVista kind of had just launched and was starting to see significant increases in traffic because, it actually provided, a pretty comprehensive and very fast search response, search sort of experience to people. And people like that. It had kind of nice, powerful operators, like you could do combinations of ands and ors. So good for kind of power users who want to do that kind of thing. And it ran on these very high-end DEC alpha system things that were kind of refrigerator-sized things. And when I joined, there were a few of those scattered throughout the hallways of DEC Whirl, where the hardware was. And then over time, another one would show up as more capacity was needed to handle the queries, and then another one, and another one, and another one. And eventually it got so that, we were touching them everywhere in this giant, in the office space we were living in. So for example, the weight room suddenly became taken over and turned into an AltaVista machine room, and you had to be kind of careful if you wanted to use the weights to avoid kicking out the plug on one of these alpha stations as you kind of tried to use the equipment. Eventually, they moved out and became a separate spin-off from DEC to be a standalone company. And so I was still at DEC Whirl, and I collaborated with them a little bit. But it kind of whet my appetite for working on search as an interesting problem domain, because it combines lots of interesting distributed systems and scaling and performance issues, as well as information retrieval in a sort of product that is incredibly useful, I think. So I decided I would do the Silicon Valley thing and join a smaller startup. So I joined Google in '99. And when I joined, there were about 25 people. We were all kind of wedged in this small office space above what's now a T-Mobile store in downtown Palo Alto on University Avenue, if you're familiar with that. And one of the things Google felt was that having lower cost computational platforms would enable us to have a larger index, be able to afford to spend more computation on each search, and so we could run more sophisticated algorithms, to have a larger index, to have an index that's updated more frequently. Computation sort of helps with all these things, and so we really focused on using commodity PCs instead of higher end workstations or mainframe kind of DEC station kind of things, because we felt that gave a much higher performance per dollar sort of return. Because commodity PCs are where all the economies of scale are. Now, at that time, commodity PCs didn't really have a lot of nice features that you might like parity or ECC memory. The disks were not as reliable. They obviously don't have redundant power supplies. But we also felt like instead of buying PCs, we could just buy the components and assemble them ourselves. And so we landed on this as an initial design for the first set of machines we decided to build ourselves. And it's not exactly a thing of beauty. One of the things that it had was basically each one of these rows, levels in the rack, was a kind of cookie tray-like thing with 4 bare motherboards plopped on it with a layer of cork to insulate the motherboards from the metal cookie tray. And then a single power supply shared by all 4 of the machines. And if you look here, you can see like the 4 reset switches for the 4 different computers at each level. Turns out sharing a power supply among 4 computers does save costs, but it's kind of annoying from a systems perspective. Also, the use of cork can land your computing platform in the Smithsonian. Very excited, yes. We all know cork is an essential part of computer architecture. And at modest scale, like a few racks of machines, you can basically just treat these as separate machines and kind of be your own sysadmin for how you want to manage them. So for example, early days of Google, we would run commands like this for M in like this giant list of machines. These are machine names, A7 through A8, A9, so on. A24, do SSH to that machine and do something. And then, when that's all done, you're done. Now, it's kind of annoying because machines fail. And so you notice A11 and A15 are not in this list of machines, probably because they died or they're being used for something else or something. So this was like pretty primitive. It's sort of like very archaic and error prone and not good. So at the larger scales, this becomes pretty untenable. And so all of a sudden you don't want like scripts with 2,000 machine names in them. So this is kind of the next generation of machines, and we got a little bit better at making nicely packaged machines, and all the connectors are on the front, unlike the previous iterations. So you don't have to like kink your Ethernet cable to snake it back to the back machine. There's a little bit of a additional cooling boost to the data center that we're renting space from, because they hadn't really expected us to pack as many machines in here as we did. So we bought some fans at Target and helped them out a bit. And as you start to scale up, you start to realize that there's all kinds of things that can go wrong when you're operating clusters of thousands of machines. So this is kind of a typical first year for a new Google cluster of machines, which is maybe 5 to 10,000 machines. You're going to have lots of different things that can go wrong. Obviously lots of individual machine failures and hard drive failures, but you can also have like entire racks go offline more rarely. A bunch of rack failures, and network rewiring is something. Slow disks. Often the things that are worst are things where things don't completely fail, but they just start like reading the disk at half a megabyte a second instead of 100 megabytes a second. But it still does, internal retries and makes it all work. And you get to see all kinds of interesting things that cause bad things to happen in the cross data center space, like wild dogs and sharks and dead horses and drunken hunters. All of those have caused outages of data center links. Dead horses, for example, comes from someone digging a grave for their horse a bit deeper than expected and obviously severing fiber. And drunken hunters comes from hunters sitting across a valley and saying, I bet I can hit that thing on top of that pole. And turns out that's a fiber repeater for a network link. Okay, so given this, it's important to be able to innovate in the actual computing systems that underlie, that sit on top of the hardware. So I'm going to outline kind of a series of steps, but all have this kind of common theme. And the theme is really, we'd like to provide a higher level view than a whole bunch of individual machines. So we want to self-manage and self-repair as much as possible. So we have our bare hardware down here at the bottom. And one of the first things you'd like to do is abstract away from individual disks. I don't want to care that my stuff is stored on the third disk on this machine. I want to be able to just reliably store stuff in a distributed file system across my cluster of machines. And in particular, the cluster is pretty big relative to distributed file system work of that day. So we need something that's going to work and manage, 10,000 machines, each with, 1 to 8 disks. And there's obviously a long history of distributed file systems. Xerox Alto, NFS, AFS, XFS, Petal, and Frangipani are all kind of interesting variants of these things. Most of them were not thinking about the scale of number of servers. AFS was thinking about lots of clients, but not necessarily, as many raw disks as we were having to deal with. And so my colleagues, Sanjay Ghemawat, Howard Gobioff, and Shantanu Young, and I kind of participated on the side a little bit in the design, but mostly they ran with the design and implemented everything, came up with Google File System, or GFS, which was an interesting approach. So we had a centralized master that manages all the metadata for the system. So all the file names and locations of different pieces of the file are managed centrally, but then the actual storage is stored on all these different disks on all these different machines. And so when a client comes along, they talk to the master to get some information about where the files that they care about are and the pieces of the files. And then they talk directly to the distributed file system chunk servers that are, and the nice property that has is you can have thousands of clients reading and writing directly to and from these thousands of these disk serving processes on the machines with the actual data. And so you have this huge I/O bandwidth that is really, really hard to get in, say, commercial file systems of the day, or really other kinds of file system designs of distributed file systems at the time. And so one of the things that a few of the design decisions were we were going to make file chunks that were quite large because we were optimizing for quite large files. The files we were trying to store were like a collection of all the files that this crawling machine had encountered during the day. So they were, many, many, many gigabytes in size usually. And the files were broken up into chunks of 64 megabytes, and each one was replicated on 3 different servers. So you have 3 possible locations to read from, and also you have 3-way replication so that if any one of those disks or 2 of those disks fail, you still have your data. And so that gives high fault tolerance and automatic recovery, high availability. So if one of the racks, for example, dies temporarily, the system can quickly try to make a 3rd copy of everything that's down to 2 copies, or even make a 2nd and 3rd copy of something if you're down to 1 copy of a particular block, and keep things reliable and available. And so that meant that all of a sudden, the disks in the data center basically became self-managing, which was a huge operational win, and meant we now had this piece of infrastructure to build on and could use and reliably kind of treat the whole data center as a disk or as a file system. And a successful design pattern that we've used in many other places is this centralized master for metadata and control, but having thousands of workers and thousands of clients. So this master tends to get these relatively infrequent tiny messages and tell this client, hey, you should go talk to this worker. And so with that, you can have this huge communication I/O capability, but still have a simple centralized master for managing the metadata. Once you can store this data, then you want to be able to process it efficiently. And so large data sets kind of imply a need for highly parallel computation. One important building block was scheduling jobs with hundreds or thousands of tasks. You want to be able to parallelize things quickly and say, hey, please run this on 100 or 1,000 machines and let me know when it's done. And there's a bunch of approaches. One is virtual machines. We used what is now called containers, but basically akin to a virtual machine, but at the process level rather than the whole OS. So we run the same OS and then run a bunch of separate processes in containers that enable us to multitask and the usage of the single machine on many tasks. So virtual machines is kind of something that is more commonly used for sharing machines these days. The early work was done by MIT and IBM. It was reinvigorated by Ed Bugnion, Mendel Rosenblum, and others in the late 90s at Stanford, where basically this can simplify utilization of multiprocessor machines because all of a sudden you can put hundreds of virtual machines on a single physical machine and allows consolidation of these servers and more efficient use of the underlying compute resources. And the raw VMs are now a key abstraction offered by cloud service providers, of course. Cluster scheduling systems are super important. So you want to be able to place containers or VMs on physical machines. It's a similar problem to earlier HPC scheduling and distributed workstation cluster scheduling systems. So Condor, for example, is a nice example of some early work in this space. There's many of these systems, so I'm not going to go through all of them. At Google, we use something called Borg, and there was an unpublished predecessor by Percy Vang, who's now faculty at Stanford, myself, Olcan Zoşarımoğlu, and others that we built called the work queue that Borg kind of took a lot of design elements from. And then there's a whole bunch of other ones. And I think there's this tension when you're trying to share a machine of multiplexing resources and performance isolation. So sharing machines across completely different jobs and tenants really gives you effective utilization of the machine, but it leads to these unpredictable performance cliffs because all of a sudden you'd like to be able to burst and use the whole machine, but other things are running there and they might be also wanting to, consume some CPU cores or thrashing your cache or whatever. And isolating while still sharing is a pretty complicated thing at the single machine level. And when you have complicated distributed systems that are, maybe a request comes in and then you're making sub requests to hundreds or thousands of machines, controlling the tail latency becomes very important. So, we've developed a series of techniques over the years. My colleague, Luis Barroso, and I published a paper in 2013 about some of those techniques. But controlling tail latency is important, and you can do things like send out redundant requests and let whichever one finishes first, win, and that can help tamp down a lot of the outliers that you sometimes see in these shared systems with performance flips. Okay, higher level computation frameworks. So give the programmer a higher level abstraction for computation. This is a general trend that has been pervasive throughout computing for its entire history. And one of the things you'd like to be able to do is give a high-level view of some computation you'd like to express, and then have a system that can map this computation automatically onto a large cluster of machines. And so this is what led us to develop the abstraction of MapReduce, which kind of builds on the sort of functional programming ideas of map and reduce, but really is about the implementation of how do you take something expressed as simple map and reduce functions and then hide the messy details of, and then sort of run the computation on hundreds or thousands of machines and hide details like locality, like you'd like to run some computation on the machine that actually has a copy of the data that input, the input data that piece of the work is going to be processing. You'd like to kind of schedule all these things across the whole cluster, deal with what happens when one machine or 10 machines fail, what happens when one machine is being slow, and so on. But this abstraction makes it really easy to do a really wide variety of large-scale computations because the abstraction is actually pretty general. If you squint at a lot of problems, you can sort of see how to express them as some combination of map and reduce operations, or maybe some chain series of those. Hadoop, when we published the MapReduce paper, we figured someone would develop an open source version of MapReduce. We weren't easily able to sort of open source the version we'd written because it was entangled with a bunch of other internal Google libraries and so on. And we figured publishing the paper would cause someone to create a open source version, and so Hadoop is probably the most popular of those. And it's nice to see people using Hadoop externally. And there's also been a succession of higher level computation systems. So Dryad by Michael Izzard and others uses general data flow graphs rather than just the more restricted map and then reduce kind of abstraction. A bunch of things like Sawzall, which is a sort of higher level language that you can implement on top of MapReduce. Dryad Link is similarly something on top of Dryad. Flume is kind of a general purpose data flow graph processing system as well. Pregel is specialized for graph compute. Spark deals with in-memory working sets well. There's a lot of interesting innovation in this space, and I think the general theme of how can you make it easy for a programmer to just express what they want rather than express how to do it and let the system figure out how to do it is a really important one. Another need we saw over time was that many applications need to update some structured state with both low latency and really large scale. And so you want kind of this abstraction of some table of state with different columns for different kinds of things. It looks a little bit like a database, or like if you imagine a giant spreadsheet that can be stored on thousands and thousands of machines. That's kind of what you might want. And you might have hundreds of petabytes of data. You might have tens of millions of requests per second. And the desires you have are you want to be able to spread this across many machines. And also to be able to grow and shrink capacity of the system automatically. If I get more data, I want to be able to add 100 machines to the 1,000 I already have serving and sort of have the system suddenly start to make use of all 1,100 machines in an effective way. And then obviously machine failures are a big thing, so we want to handle those as quickly and transparently as possible. And you often prefer low latency and high performance over consistency. So there's been a bunch of distributed sort of semi-structured storage systems over the years. Bigtable was the system we built at Google. Fei Chang and many others, including myself, published a paper in OSDI 2006, which is relied on using GFS as the backing store, but then had this higher level model of rows and columns and timestamps. Sometimes you want to be able to see versioned history of each row and column, and so that would prove to be pretty convenient. And no cross-row consistency guarantees, so we did not implement distributed transactions in that system. And the state was managed in small pieces. So imagine the rows are sorted and we break it into like tablets of 100 megabytes or so. And recovery was fast. So there were tens or hundreds of machines and they can each recover the state of one tablet. So if a machine is serving 100 tablets and that machine fails, the controller of the system can all of a sudden notice that and tell each of 100 other machines to each pick up one of these tablets and recover quite quickly. Dynamo was a system developed at Amazon by Dikendia et al. Had versioning and app-assisted conflict resolution, pretty interesting kind of approach. Spanner is a system that we built that was sort of the natural evolution of Bigtable, but changed a number of things. In particular, a single instance of Spanner was designed to run across many, many data centers, potentially one instance for all of Google. Although in practice, we have a handful of different instances. It supports both strong and weak consistency and includes distributed transactions in the programming model. So another successful design pattern used by both MapReduce and Bigtable and Spanner is give each machine hundreds or thousands of units of work or state. And this can help a lot with both dynamic capacity sizing. If you want to add a bunch of machines, all of a sudden, most of the other machines in the system can shed a little bit of load and give it to the new machines you've added. Helps with load balancing. So if this machine is a little overloaded, I can take 3 things away from it, so it now has 94 things instead of 97, and now its load goes down a little. And the faster failure recovery thing that I mentioned, where if the machine fails, 100 other machines all in parallel help with recovery because they each pick up one of these units of work. The public cloud has been like this amazing innovation of making a lot of these systems available to developers. Many of the systems at Google that I described, we built for our own internal developer usage, and we're now making them available to external developers. But many other cloud providers are also, creating really interesting APIs that developers, not just within those cloud companies, but everywhere, can build on and really kind of quickly build really interesting large-scale applications. I think I'm going to go a little faster through this. I think people know what cloud providers are. I'm going to talk instead about how machine learning is transforming computing. So one of the things that has really happened in the last 10 years or so is the emphasis of using machine learning for all kinds of different things. And the kinds of computations you want to run with machine learning, in particular kind of neural net-based computations, have 2 really nice properties for designing hardware that is more specialized for that kind of computation. In particular, reduced precision arithmetic is often just perfectly fine, so 1 or 2 decimal digits of precision rather than many. And most of the popular machine learning models that you see solving real-world problems these days are composed of a handful of specific operations in different orders and different sort of flows, but really they're essentially composed of low-level linear algebra kinds of operations, things like matrix multiplies or vector dot products. And so if you can essentially build machines specialized for doing reduced precision linear algebra, then you can suddenly have tailored hardware that is much more efficient because that's all it needs to do rather than general purpose CPUs. And so there's been a rise of more tailored computational devices, starting first with GPUs, as people started to realize that GPUs could be used not just for graphics, but we're also pretty good at building, at doing the kinds of computations described here, where you want to be able to do machine learning oriented general purpose computation. And then one of the things we wanted to do at Google is we realized machine learning models were going to be really important. We wanted to deploy them in lots of places and also build larger scale systems that will enable us to train more powerful systems. And so the first TPU, or tensor processing unit, that we built was a Google designed chip for neural net inference. And so this is kind of the chip. This is a rack of the machine, machines with those boards in them. And this is actually the machine that was used for the AlphaGo competition. And so when our DeepMind colleagues were playing the matches of Go against world champions, they were using these actual 2 racks of machines. We put a commemorative Go board on the side. But they're also used on every search query for machine translation, for speech, for image recognition, and so on. And there's a ISCA paper about the original TPU there. Oh, yeah, there's our Go board circle. And the second generation of system that we built was really designed for both training and inference. So it was built out of these boards, which you see contain 4 chips. And the really nice thing about TPUs is if you peek inside, the design is actually remarkably simple. So it has a giant matrix multiply unit for most things, which are the bulk of the compute operations, or the bulk of the cycles, at least, in machine learning operations. Has some scalar and vector units for things that are not matrix multiplies. It has HBM, which is a high-speed memory system. And that's about it. That's one of those chips that has some HBM and 2 cores that are each relatively simple. And has quite high memory bandwidth and reduced precision arithmetic. And then the third generation looks kind of like the second, except its clock rate is cranked up. It's a little more optimized from an ASIC design standpoint, and it has water-based cooling. And these systems are designed to be connected together into larger configurations called pods. So this is the TPU V2 pod, the V3 pod, which is the 1,000 chips connected together into a 32 by 32 2D torus, which is more than 100 petaflops of compute. And these are available both internally at Google, and also we make them available through our cloud services. I think I'm going to skip this, but there's an early peek at TPU v4 in the MLPerf results, so we're really, really excited about TPU v4. I'll mention a system we used for MLPerf, which is an open benchmarking setup for measuring the performance of machine learning systems. We actually just built a 4-pod out of cabling together a bunch of single pods, and did pretty well there. And there's a whole bunch of nice models that run on these systems, so people can really quickly take advantage of them. The other thing I'll point out is it's not just data center scale things, but machine learning is really shaping the kinds of things you want on edge devices like phones or other kinds of very small scale, low power environments. And so edge TPUs are sort of similar design philosophy, but designed to run in a really small power envelope. And a lot of the progress and widespread use of machine learning has been driven by a progression of ML frameworks. So I'll just highlight some of them. So Theano was kind of an early innovative machine learning framework from University of Montreal. James Berkshire and others published, but it's been worked on for many years. Torch was a Lua-based system that Ronen Colabert and others worked on, starting and publishing first in 2011. TensorFlow was a system that we built based on our experience of a first-generation proprietary system we built internally that we didn't publish about, and also taking some lessons from Theano and Torch. PyTorch is sort of a Python version of Torch that Facebook and others have been collaborating on. JAX is a system built at Google that's designed to make research really easy and expressive, paper published in 2018. So I think the ML space is moving quickly, and the progression of frameworks is also quite good. TensorFlow has a nice emphasis on both research uses, but also production uses in both large-scale data centers and more edge devices. PyTorch is a little more focused on expressivity and research, and is also kind of has a rapidly evolving and more fully thought out production stack that they're working on. Okay, so I think I'll just finalize by talking about what I think we want going forward in the machine learning space, which I think is an area I'm certainly, I'm really excited and working personally on this kind of project. Is I'll just highlight all of these. I think one of the major problems we have in machine learning is that we tend to train new models separately for each new problem we care about. And we start from scratch, really scratch. I mean, like we literally initialize the model with random floating point numbers and then start training it. But instead, I think a much better approach is to have a very large model that can solve many tasks. And then when we have a new task, we can learn how to use the expertise the model has and leverage it for the new task. And so a cartoon diagram of how this might look is we have a machine learning model here built up of lots of different components. A component is some piece of ML computation with some state and some operations. We've kind of maybe already trained it to do these tasks. And now a new task comes along. And we can search over what are the possible components that we might want to use in order to solve this task and how might we want to use them. And maybe we come up with this way to use a couple of components that get us into a good state for this new task. Maybe we want to do even better on this particular task. And so we introduce some brand new component to the system, give it a bit of additional capacity, and then can search and start using that component and start training that component to do this new task. And maybe that component is running, something where it kind of adapts to the way in which it is being used and kind of wires itself up to specialize for the kind of flow of things going through it. So I think this is a pretty interesting direction to go in. And all this stuff would be then mapped onto large-scale machine learning hardware like the TPU pods that I just showed you. I think there's a great combination of kind of systems level challenges, machine learning challenges, and software engineering, structuring challenges here that are going to be really interesting. And with that, I will stop sharing my screen and take a few questions.
Thank you for that, Jeff. I will ask. I have one right now from the crowd. We can gather some more. So this is one that came from somebody that said, should we be still looking for tail latency root causes at the end hosts or core networking infrastructure? Which abstraction would be a really correct abstraction to alleviate the tail latency problem at the moment?
Yeah, this is a good question. I mean, I think one of the things that has come up over the years is there's a really, really wide variety of things that can go wrong and cause tail latency issues. And so focusing on techniques that tackle any one of those things or a few of those things is useful, but it's not going to solve all the problems. The myriad set of reasons that tail latency can increase is just too broad to really have a single hammer that really fixes all of them. And so I think you want techniques like being able to send redundant requests to multiple places and have them race and take the results of the first one, which is a very general technique that deals with a whole bunch of tail latency kinds of issues. So if that machine is slow, or if it's down, or if the network is slow and it drops packets on the way to one of them but not the other, that's covered by that general approach. So I would say emphasize general approaches that are going to deal with lots of different sources of latency, and not ones so much that tackle any particular one. Although, obviously bringing down average latency for a particular thing is always going to help.
I had done a lot of work in, because I used to work at Comcast, and we used to do a lot of work with trying to like put, and this actually goes to Irene's talk coming up next, like putting more resources into doing stuff in network, doing more programming in network, right? And you've seen there's a lot of papers now, of course, at Usenix conferences that also are showcasing how we can do these things and use machine learning techniques and whatnot. So I guess in some of the things is at Google in particular, how like, I guess, where do they see doing things in network versus doing things obviously we're talking about a lot of these chips that we're doing, but I guess where does it come in where you can leverage the network more versus leveraging the machines more themselves at the data center level, and kind of where do you kind of see that kind of happening where like take advantage of hardware, I guess, at the most?
Yeah, I mean, I think there's a lot of opportunity to move computation in different ways than we've sort of got it organized today for the most part. I think being able to run sort of computations for ML on the edge devices rather than in the data center is one example where, you want processing really close to something like some camera that you might want to run a vision model on the camera itself and send back not just the pixels, but maybe, only the pixels when something interesting has happened. I think that's an example. I think being able to specialize hardware and sort of run those specialized algorithms on hardware that is more tailored for the kinds of things you want to do is important. I think the machine learning hardware explosion has happened because there's a abstraction now that's general enough to capture a whole bunch of things. And so it makes sense to focus on building specialized accelerators just tailored for machine learning because it's a super broad area. But I think if you could make chip design much, much cheaper in terms of effort, you would see more of a proliferation of chips specialized for this and that. And then all of a sudden you have, kind of a very heterogeneous system of different processing elements that are good at different kinds of things throughout your network, throughout your distributed system. I think if you look at modern SoC designs, even a lot of those are starting to look like very heterogeneous collections of IP blocks that are good at different things. So they have JPEG decoders and neural net like modules and general CPUs and things like that. I think more heterogeneity and more processing in network or in various far-flung places in an overall system is a trend that's here to stay.
Oh, cool. That's yeah. I've thought that as well. It's a good answer. So we have a lot not coming in the chat now, so I'll start getting to these. Someone asked, do you see all first-party services in companies such as Google run in pure SLO-driven fashion, i.e. teams will have to develop services that will have to give guarantees about their worst-case processing time to other services?
I would say we are not quite so formal about that for everything. We definitely care about the latency for high-level services and the services those services build on. And we generally don't give hard guarantees. We give distributional guarantees. So we will say the 99th percentile latency of request to this thing will be, X. But we don't give kind of hard real-time guarantees that absolutely every last request will finish in, X milliseconds. But those distributional guarantees are kind of what we will generally kind of promise. We look very carefully at different services and what their 50th percentile latency is, what their 90th percentile, 99th percentile. And that's important for people who are building on top of those services to understand the performance characteristics of those.
Oh yeah, that makes sense. Okay, got another one in here. How large can those large-scale ML models get given the interconnect limits of, for example, TPUs? Or alternatively, is the notion of a large-scale model more of a way to think of a particular ML jobs or a particular ML jobs being able to choose existing components off the shelf, like any other software dependency, and then deploy an optimized model to a limited number of TPUs?
Yeah, I mean, I think first, obviously, when you have lots of computation in many different devices, more bandwidth between them helps. And so I think the TPU systems have tremendous bandwidth between the different chips in the system. And so in the pods, part of the reason those pods are so fast is the chips themselves are fast, but the interconnect is also super high performance and designed for the kinds of things you need to do in large scale ML training and inference. So having lots of bandwidth helps, but having even going beyond a pod boundary, you definitely want a lot of data center bandwidth so that you can sort of build systems out of components like full-size pods as building blocks. And then the kind of ML components that I described, you would get mapped onto different parts of those pods, or maybe a whole pod, or a 4x4 chip slice of a pod, and communicate with other ML components with the highest speed networking that is available to them. So that if they're on the same pod, they would use the sort of special pod network. If they're across in a different place, then they would use the data center network to communicate things.
Gotcha. Cool. So another question, kind of getting on this, like things emerging. Any thoughts on how emerging persistent memory technologies will change large scale infrastructure? General question, but it's a good one.
Yeah, I mean, I think anytime you have something that is got very different performance characteristics than what has existed in the past, or properties, and in this case, the combination of in persistent memory, my understanding is it's basically not quite as fast as DRAM, but within some small integer multiple of DRAM bandwidth and latency, but is persistent, right? And I think if you have something like that, you would design your higher level systems very differently than the systems that have been designed for the case where you have DRAM, which is volatile, and then much slower devices like disks originally, more recently flash, which is kind of between disk and DRAM and nice in terms of seek time relative to disks. But I think that will change what you want to do. It's important to keep an eye on the performance characteristics and other design properties of your basic building blocks and evolve higher level designs to take advantage of those things.
Cool.
A similar argument can be made for understanding the computational building blocks of ML specialized hardware versus CPUs, right? Like how do you build heterogeneous systems that take advantage of the properties of both of those kinds of things?
Cool. Yeah, that makes sense. So we have two more if you have time for that. I think that would be good. Cool. So we have a question that says, Google's already leveraging precise clocks in some of its services. So we have a clocks question. You got to have a clocks question. It has to happen.
We've got time.
Leveraging precise clocks in some of its services like Spanner, which makes designing distributed systems much easier. Do you plan to expose such an interface to third-party developers?
That certainly would help third-party developers. I agree. I am not that closely in touch with exactly what the plans are for TrueTime as a service itself. But it would make sense as a product, I think. But I'm not sort of deep in the product plans for whether that might exist or not.
Cool. And we'll go with one more, which is we just got in. How do you foresee all of the available non-CPU machine learning acceleration hardware being abstracted for use in inference? Do you see higher level frameworks for producing FPGA bit streams from ML models maturing in the near future? Do you see a use for kernel bypass, which we're going to have some talk about that coming up, kernel bypass for acceleration devices?
Yeah, I mean, I think it's a good question. There's definitely this Cambrian explosion of work on different kinds of accelerators for machine learning computations, some of which is focused on inference, some of which is focused on training and inference. Some of that has properties like it has a whole lot of SRAM relative to the normal amount of SRAM you can get. And so if your model fits in the SRAM there, it gets tremendous performance, but if it doesn't fit, then it kind of falls off a cliff. And I think for all this plethora of different kinds of hardware, we do want abstractions that can map computations onto a wide variety of those things, because you obviously don't want to hand code, assembly language for this one, or like low-level code for this thing, and then you want to run it on something different and have a lot of redundant effort there. So things like XLA, which is a compilation framework we've put together at Google to support TPUs and CPUs and GPUs, are pretty useful. MLIR is kind of a higher level abstraction for expressing a lot of these kinds of computations and doing high level transforms that make sense across a wide variety of devices. And then you would have kind of a traditional retargetable compiler that kind of can map to different ML hardware devices. That's sort of where I see that going. Like, retargetable compilers for CPUs are generally a thing, and we make use of them. So I think the direction we will evolve is having something more like that for how to map ML compute onto ML accelerators.
Well, thank you so much, Jeff. That was it's a super insightful talk. It's great history. It made a lot of us, I think, reminisce about some times for some of us who've been around back in the day. I was really happy to see Alta Vista. Peter Alvaro talked about his some story about Ask.com that came up. And of course, all the future directions you're all working on. Obviously, there's major hardware, software at this whole thing, which is really great. So thank you so much for joining us for this event.
Yeah, thank you very much for having me. And everyone should support Usenix. They run a great conferences, and please do support them. Thank you.